So we know that there's a 42% chance that any stock we select increased in value. How likely is it that 2 out of those 4 we selected increased? Well, we're going to use the binomial formula for that. We're going to say, well, how many different ways could we have that outcome? Well, the first and second stock we selected could be the ones that increased. The first and fourth could be the ones, the third and fourth. We're going to use a combination question. How many combinations of 2 are possible out of 4? We know the answer to that is 6. We could also just use the formula. And then we're going to multiply the probability of success, 42%, time raised to the second power, because we want that to happen twice. And then we want to multiply that by the probability of not increasing, 58%. And we're going to raise that to the second power, because in this scenario we want that to happen twice. Does that make sense?
Yeah.
Yeah, just if you could, just write that down, just work that, I'll do it in a minute after I erase some stuff on the board. But to just actually write this problem using the binomial formula on the previous 2 pages back. Like actually just write out what you would put in that formula on page 5. Okay, our P, probability of success, 42%. N is 4, because we're picking 4 stocks. The number of times we want to be quote-unquote successful here is 2. Okay, so probability of exactly 2 successes equals. All right, what goes here?
4.
4. Anything else?
Oh.
Factorial, yes, over 4 minus 2 factorial, 2 factorial, times 0.42 exactly, raised to the second power, times 1 minus p, 1 minus p, yep, 0.58, raised to the second power, and that's it. And if we crunch that out, we will get something very close to 35, 36%.
So I'm having a hard time figuring out the variables. Like the math is, I get the math, but just understanding the different variables, which the components. Like, can you walk me through the process?
Yes. So, we've got, we're reading that 42% of stocks advance. So that's the chance of success. We don't need to worry about that 3,500. That's just giving us the way they got the 42%. And the question asks is if you've randomly chosen 4 stocks. So we're going to randomly choose 4 things. So we have 4 trials, if you will. It's like we're rolling the die 4 times. Except it's just a die that's like gives us a 42% chance of hitting. So there are 4 total events happening. So N is 4. And then the second part of the question, which we started with, exactly 2 of the 4 stocks you selected increased. It's the number of successes you want in this experiment. So X is 2. Okay, this makes sense? All right. So take a look at the graph on the bottom of page 7. You see we've got a discrete probability distribution. this is an answer to the question of, on the vertical axis, we've got probability on the left-hand side.
to solve this?
Oh, yeah, you can if you want. What'd you get? What'd you get?
Yeah, I'm not finished, that's why.
Yeah, don't worry about it, don't worry about it. You get like 36% or so. Yeah. And the answer is gonna be at the bottom, is that graph at the bottom of page 7. So, if we were to graph all these possibilities, we would have this probability distribution. On the left-hand side, we have probability. On the horizontal axis, we have number of successes. So you can see number of successes. We could pick 0 stocks that increase. We could also pick 1 stock that increases, 2 stocks, 3 stocks, or 4 stocks. And it's giving us the probability of an increase each time. Does that make sense? So this is an important step here. I'm introducing a probability distribution, and I want to make sure you're comfortable with it. So on the left-hand side, we've got probability, the chance of this thing happening, and on the horizontal axis, we have number of successes, 0, 1, 2, 3, or 4. So we've got kind of a curve there. Most likely thing that would happen is we would choose 2. Choosing 1 stock that advances, that's also fairly likely. And then 0, 3, or 4, we're getting into less likely scenarios. Okay, so everyone comfortable? This is a probability distribution. We'll be seeing a lot more of these in class. And we at least have a sense of how to approach the binomial distribution. All right, let's continue with that binomial, and let's do this quick experiment where we're using the binomial probability distribution, and we're going to use this to answer this question at the top of page 8. Suppose we have an experiment where we flip a coin 20 times, and we count the number of times the coin comes up heads. All right, so what's your name? Gabriel. All right, so Gabriel, we have an experiment, n equals 20. 20 different things that are going to happen. We're going to flip this coin 20 times. The probability of it coming up heads each time, 50%. I'm going to ask you all to calculate the probability of the coin coming up heads 0 times, all the way up to 20 times. So let's pick one in the middle just to think about. What's the probability of you flipping heads 8 times out of those 20 possible flips?
Isn't it half times 8?
What's that?
Would it be 1/2 times 8?
No, it would not, because you're going to have 20 total flips, because you need to consider the different combinations of ways that could happen. The question you're giving me the answer to is, what's the probability of flipping a coin and having it come up heads 8 times in a row? The answer to that is what you said, 1/2 times, 1/2 to the 8th power. So, all right, we've got 20, we're going to flip this coin 20 times. And each time there's a 50% chance it comes up heads. What's the probability of me getting exactly 8 heads? How do I solve this problem?
Binomial.
Yes. First thing I need to know is how many different ways this could happen. I could get heads the first 8 times in a row, and then the next 12 times I get tails. Right, you get heads the first time, the third time, fourth time, this 12th, 13th, 14th, as long as it adds up to 8. How many different combinations of 8 of 20 things total are there? So, P is 0.5, N is 20, X is 8 in this iteration. Okay, so probability of 8 equals 20 factorial over 20 minus 8 factorial times 8 factorial times 0.5 raised to the 8th times 0.5 raised to the 12th. You like that?
Oh, 20 minus 8.
Wait.
Yeah, the other calculators.
Oh, I
think
get it, I
20
get it.
factorial in my phone calculator. Doesn't do
20, you can't do 20 factorial? Wait, do you have a cell phone?
Yeah.
Yeah, so you do 20 and then x factorial. And it's 2.4 times e to the 8th, it's e to the 18. So it's like multiply that by 18 zeros. I think that might be it.
So that's 2.4.
No, it's 2.4 times e to the 8th. I don't know what that means. Divide it by 1,000,000 and see what happens. And then keep dividing it by 1,000,000 and then you'll get you'll hit on a manageable number. Yeah, you're just gonna have to get used to that particular thing. Can you keep that in your calculator and divide it by whatever you get down here? And then maybe you'll get a manageable number?
That's just my way of,
Sometimes it.
does that make sense for you? I wrote that on the side here.
Alright, does someone have a way of solving this with their calculator?
I don't know how to do this. What's the factorial function on the calculator? Does it show up as the exclamation point?
Yeah.
Yes,
Yes.
usually does.
It does?
Maybe that's gonna be under like a math function. Yeah, that'll probably be under a math function. Is there math? But-
That's a huge
It's what
This is what you got to go for.
So if I divide by 1,000,000, big number.
But it's an actual number.
Yes.
Okay, yeah, right, so now we're
Number 2.
So, yeah, so it's
Can't figure out
this
the factorial.
plus 6 zeros. That's the answer.
Oh,
And it was
okay.
Andrew. So maybe if you keep that big number in your calculator and divide it by whatever you get for this, then it'll come out to a manageable number on your calculator. Okay. So let's just solve this. I do sometimes like to do this thing where I try to give individual people a chance to solve 0 through 20. If we just solve this, I would be happy. Does anyone have an answer? You got 12%? Okay, close. Close.
What I gotta hear is scientific. I'm gonna put this to the top power.
Alright, so 20 factorial.
It keeps giving me that plus 8, E plus 18 crap.
Yeah, that's just how many zeros you need to add
10
to it.
zeros after.
Yeah, yeah. So divide that by, see if you can you divide that by, use parentheses and divide it by 12 factorial times 8 factorial? Or maybe, better yet, maybe you can, no, you're gonna get some large number. Okay, alright, so this is the kind of thing I would like you to go home and practice using your calculator to solve. You could also use Excel There definitely be a way you could do it there. I can work with you in your calculator a little bit after class, but we're probably gonna be tired and frustrated and wanna go home. But I will stay if you wanna do a little calculator work after class. But you're just gonna need to figure out how to work your calculator to solve this kind of problem. And if you're getting that big E, big whatever,
Well, the
you
factorial I got.
need to figure out a way to keep that in your calculator and get
Is
into
it
it.
supposed to be in a trillion?
This will be in the trillions.
That's,
But
that's
the
204 trillion.
The ultimate answer will not, because you're gonna be dividing it by a really big number. This would be like a trillion.
Yeah,
What did you get?
trillion in that?
125,970.
125,970, okay. So then can you multiply it this times this?
Yeah. Just figure that out.
This one's better?
Yeah, I can do the more function.
I found a calculator online and it came out
I got the numbers for those.
to .12. You said that right?
0.5 to the 8th power is 0.0039.
You said it's a little thing up like.
Yeah, it's an up arrow.
The answer, is the answer .1201? No?
I did it like 0.17 something. Yes.
To get that, can you just do 20 factorial divided by 12 factorial, right?
Times 8 factorial, can you do the time? Yeah, 20 factorial divided by 12 factorial
And then that.
times 1 over,
And that, no, what I did was I got that same.
divided by,
Then I
divided
divided it by the 8 factorial
by,
again.
yes. Yeah, try this in your calculators, right? 20 factorial divided by 12 factorial divided by 8 factorial.
I got 125, yes.
Yeah.
Put in parentheses, the bottom, it will go.
Parentheses is another way to do it, or the way to do it, your neighbor does it, one at a time would work too.
Yeah.
Right, so you were
I'm
doing
working
this?
out the, yeah.
Yes.
Divided by four.
I just want to know.
Do you want to do 20 factorial divided by 12 factorial
Yeah.
divided by 8 factorial?
Yes, you got it.
25,970.
Okay.
I did it wrong.
And then,
And then multiply it by 0.5 raised to the 8 times 0.5 raised to the 12.
That astronomical
This is
number.
12, I wrote this, I
Divided
wrote
by 12
it, it's supposed to be 12.
It gives me 0.120.
And then divided by 8.
You want the whole thing?
1, 2, 0, 1, 3, okay.
Is
Okay.
it .098,
That's, yeah, that's the answer.
.0983?
That is totally right. You are so right. I'm so sorry. Right on.
So right.
So right, so long ago. The answer's 12%. Good job.
But that was on the chart.
Like 12%. Yeah, the
Why is
answer's
it
on the chart.
12%?
I was looking at the wrong thing on the chart, my bad.
Wait a second.
Why is
Okay.
that 12%?
Derek.
I just multiplied this times 0.5 raised to the 8 times 0.5 raised to the 12.
Okay, that's what I did.
Get from 5 to the 12.
Where'd you get 7 trillion again?
Because 0.5 raised to the 8th is .0039.
Okay, I believe you.
And then 0.5 raised to the 12th is .0002.
Okay, so multiply those
So when you
together.
multiply that by 125,970, you get .0983.
The answer is
Yeah.
12%.
0.09, so it sounds like it's close.
You gotta multiply all across.
Yeah, we did.
Yeah.
Oh, you gotta multiply all of those numbers?
Yeah.
So this times
So
this
then-
times this.
Okay, because I was just doing the 4, rounding it to the 4, so.
Okay.
Okay,
Oh,
now I see
so
it.
it's a rounding? Okay, maybe a
Yeah.
rounding
You
error.
said to round to the 4, right?
I'm just listening.
Round to the 4th for your final answer, but when you're working with numbers this big, you wanna keep them in your calculator.
Okay, that's what it is.
Yeah, no problem.
Alright, I'm a little behind schedule, but I'd like to keep going for like 10 minutes and then we'll take a break. Is that okay with you? Okay, so bear with me here. Let's take a look at the bottom of page 8. That is the binomial distribution for this experiment. So if you were to flip a coin 20 times, the chances of 8 heads, as your colleague pointed out 10 minutes ago, would be 12%. Like you can look at the bottom of that chart and see the number 8, probability of success, or number 8 successes, probability is 12%. Any of those, what's the probability of flipping 10 heads out of those 20 times? 17, yes. What's the probability of 14 heads? Yes. What's the probability of 20 heads? Extremely, extremely small. Okay, so tell me about that shape, the distribution of that probability curve. Looks even? All right, does it look familiar? Where have you seen it before?
Binomial distribution.
Standard normal? Maybe?
Multiplication.
Standard normal? Normal distribution?
Combination.
So this could be called a classic bell curve. We're gonna call it a normal distribution.
He said that.
Yes. So normal distribution, so again, I threw a lot at you quickly, and so sometimes you had some calculator issues and just working out the kinks with this, but we got there. Like, we were able to solve at least one of these, and if we spend more time on it, we could have solved all 20 of them. So this distribution, you could have calculated. You could have calculated each one, and if you had graphed it, you would have graphed the normal distribution. The most important discovery in statistics is something that you just partially recreated. You have the skills to calculate the normal distribution. Now, next question. If I were to send all 18 or 19 of you home and said, do this experiment tonight, flip a coin 20 times, write down how many times you get heads, and then we come back next week and we graph it, we put it on a graph, what would the distribution look like? Would it be this perfect bell curve?
No.
Would it be kind of close to this perfect bell curve? Maybe kind of close to this perfect bell curve. But since there's only 19 of you, maybe a couple of you would get really unlucky and only get heads 4 times. And then, it would look something like this. Next question.
Don't we have to consider the variables involved, though, like how hard we toss it and all those other things that are involved?
Great question. Do we?
No.
What about the weight, if everybody's using a coin?
We're assuming everyone's using a fair coin.
Oh, okay.
So what is the possibility of flipping heads? 50%, right? Unless you have a magic coin, right? Yeah. If you flip it really hard, does that change your odds? Not really? Yeah.
What exactly, I mean, I understand what you mean by a definition of a fair coin, but if you were actually doing an experiment, would you manufacture something, or would you use a penny or a dime? The reason I ask is because I had heard one time, and I forget which way it goes, but something that even though that you think if you're flipping, say, a penny, heads or tails, that it should be a 50-50 proposition, but because of the way it's manufactured, it's a little bit more weighted on one side than the other. So it's just like when you're using a fair coin, what exactly is your definition, or what's your example?
So we're gonna assume this coin is fair, and that there's a 50% chance of getting heads, 50% chance of getting tails. If you have a magic coin, I would love to see it. Also, if you could tell me whether or not I should guess heads or tails next time there's a coin flip, because there's a slight. Okay, so but we're gonna assume this is a fair coin. Is that fair? Fair enough? Even enough? Okay, so for now we'll assume it's a fair coin. 50% chance of heads, 50% chance of tails. I already asked you if you all went home and we graphed this would look kind of like this. Next question I want to ask, what if we sent every single Mercy College student, and there are 10,000 of them, we sent them home, told them to do this experiment, and then recorded the results? What would the distribution look like? It would look pretty much exactly like this. Why would it look pretty much exactly like this?
Bigger sample.
Larger sample.
Larger sample, they would ultimately fall into that probability. We have large numbers, it's going to match this probability. So that's the second important step in understanding this. If we were to send a large number of people home, then it would mimic this probability. That's kind of amazing, isn't it? We would know what's going to happen with these 10,000 students before we even send them home, because we can calculate the probability. So we would know what this distribution looks like. So the third question I want to ask. Now, in our calculations, we know that the most likely number of heads is 10. And that makes sense, of course. 50% chance, assuming a fair coin. 10 times it's going to be heads, 10 times it's going to be tails. We know that from our calculations. Suppose we didn't know that. Suppose we didn't know what it was, and we wanted to find out what it was. And we wanted to find out by asking those Mercy College students who we sent home. And we can't ask all 10,000 of them. They'd say all 10,000 of them do this experiment, and they write it down. But we can't manage all 10,000. We can't ask all 10,000. Suppose we just ask one of them. What is the probability that Mercy College student is going to tell us the answer is 9, 10, or 11? What is the probability they're going to tell us the answer is 10? 17%, right?
Oh, we can stay the same distribution.
Yeah, we just don't know what it is. It is the same, we just don't know what it is. We're trying to find out what it is by asking a Mercy College student. So there's a 17% chance that this student is going to tell us, well, I flipped a coin and I got 10 heads. So what are the chances that any one student is going to tell us they got a 9, 10, or 11?
16 or 17%.
So 9, 10, or 11. Add them all three together.
Forty-nine.
49%.
Yeah, 50%. So there's a 50% chance that just by sampling one student, the answer is going to be within one of the true mean. And remember, in this assumption, we don't know what it is. We don't know that the average is 10. We're trying to sample and figure out what it is. We ask one person, there's a 50% chance that we're going to get within one. So that's pretty good chances of getting close to the right number just by asking one person, right? What if we ask 2 people? Or 3, so let's say 2 people. We ask 2 people. Now, there's no quite right or wrong answer to this. Where I'm going with it is, maybe one of those students would have gotten really lucky and flipped their coin 15 times. But the other student probably was in the 8, 9, 10, 11, 12 range and would have evened out that extreme outlier, that person who got lucky. Because the chances of both of the people we ask getting really, really lucky gets to be very, very small. So remember we said the chances of getting 20 out of 20 is like less than 1%. The chances of 2 people getting 20 out of 20, extremely, extremely small. So just by adding that second person, we're able to counterbalance some sort of sampling error. So imagine if we were to ask, say, 30 students. What did you get last night when you did that experiment? Randomly, we select 30 students, we ask them all, we average their number. All right, what do you think we would get for our average in this trial? Well, the answer I'm going for is we would get something probably close to 10, just by asking 30 students. Because we know any one student has a 50% chance of telling us 9, 10, or 11. And we know we might have some outliers, but we have just as much chance of canceling out those outliers. So that's the takeaway from this graph. is that there is a distribution that it will fall into based on probability. And if we don't know what it is, we can get pretty close to it just by random sampling. Okay, so let's take 10 minutes. Let's come back at 8:25 and finish up.
Hi Nelly. How you doing today? See you. Good. Yeah. Well, good, right? Every day. Every day.
Skip this first one, right?
Yes.
I got your shirt still. How you doing? Nice to meet you. I'll see you next
I
week.
took my phone, you can speak to him, right? As soon as you can.
Yes. Yes. So this is 0, so that goes away. This is raised by 4th power. Now this is 1.
You know, yeah.
Cancels, it goes out at 1.
And this is 0 because.
Yeah, 4 minus 4 is 0.
I already did it.
And 4 minus 4 is 0.
Right.
So anything raised to 0,
Yeah.
this is 1, it just cancels out. So all you're left with is 0.42 raised to the 4th.
We'll be right with this one.
Which is the same. 0.42 times 0.42 times 0.42 is 1.42.
Now, I was signed up for that.
This one, well, doing it this way. I understand that.
I'm taking up all my classes.
You kind of lost me from this side. And then we were trying to figure out, and you multiply it by 4.
That to be my.
It's not, it doesn't.
Yeah.
You guys do.
Friday night?
Which is, it's just, I look at it, go, you didn't.
I took my thing.
See, I work in office, it's a little bit smarter for me to take exams. I think of
I think you feel like this is just something you're just gonna need to.
yeah, I figure
There's some homework problems that will walk
lights
through
are low
this.
of the 9 credits.
I can totally stay with you after class, but I think your brain's gonna be so fried by the time we get
No,
done.
I get it, I get it.
Yeah.
I mean, this is the same thing I said while I was doing college.
Yeah, so we can all find a sheet together.
So I'll just, go ahead.
Take your breath.
Yeah, okay, thanks.
You bet.
Oh, okay.
You good?
I just solved everything. Hey.
That's it.
So
You don't have to buy.
here's what I need help with. Bring my calculator next week.
Okay.
I need to know how to use it.
I just figured out how to do that, so that's easy now.
I'm going to.
Wait a minute.
You have it, if not, I gave her and then I'll give her mine.
Yeah, but I need for the vending machine, is that where we're going?
Oh,
Great to have you in class.
but I just gave,
I'm not the
no,
best.
she said now or later.
So on Blackboard,
I'm gonna practice on that.
Yes, Felicia, you better bring your money, cause I ain't got any.
Yes.
I just been right today, it's so funny that I make you laugh.
Well, I mean,
Problems.
class, you helped me in turbo. I
Yeah,
flew to that part of Khan Academy after that.
good.
Yeah, combination meditation, I know that formula by heart now.
What we're gonna do now is, just similar stuff that we did in Turbo, the C distribution.
Yeah.
The only problem is it's like the important thing, the more important thing in class, and everybody's gonna be tired,
Yeah.
but I'll try my best.
It'll be good. It'll be good. I still have my notes from this summer too, so.
Okay.
That'll help.
Oh,
Yeah.
that was Monday?
No, it wasn't, it happened to me, it was just like introduction.
I thought it was started today. I didn't do it.
Is it turned on?
It says there's no signal or something.
Kosher summary.
No, turned on.
Oh,
Midnight Friday.
not turned on.
There you go. Boom.
The summary is.
Oh my gosh. swear to God, I pressed that button like
Yeah.
twice.
It's all right.
Right here, you see these?
I believe you. It's working.
These are the questions that do not exist in my
That's right.
That's right. And he said, he wrote a thing and said, if you don't have to look at it, you can come in and
Ah, Jonathan,
What's up? No?
now it says no. I saw the Microsoft Word thing. Microsoft Office.
I've been doing that kind of thing. Put it on.
I tried putting the blue one in and then.
And you can use the box. If the has this book was given to They do.
All right.
When you register,
Okay, so Blackboard, I can go online and sign up for that.
you can get it through your and use it as an idea.
Just keep going, I'm trying to do it.
Yes.
Go to, are you going?
No.
All right, so.
Yes,
I just need
yes.
one.
Yeah.
Why is it not in this one? That's not.
Oh, yeah, well, it's one, so what's one minus 0.5?
I don't even.
Okay.
Just want to make sure, thanks.
You got it, you bet.
That's what is the number?
No, whatever password you put. You never did on
To register.
the register, yeah, what you.
Your Mercy Connect?
I mean, the Fed.
No, not password, no, when you register for classes. How you get it? They didn't give you notice and anything,
You did a form, you did.
but she didn't give you like.
No, I did do some, yeah, I did do all that.
It's that same thing.
I gotta find it.
Oh, I thought that's what I said, yeah.
Oh, take your time.
I'm just going through my emails. I don't want to look at this.
I have to email yours. It's the same thing, Brenda, if you have.
If not, I could do it.
Why is this upside down?
I gotta figure out this.
Is yours upside down?
I know I did it, but I don't remember.
Yeah, I think you could, if you call them, they really is good, like, but look, come to the table, I'll show you.
Oh, you
Oh, once you go to that.
Oh, no, you're doing it wrong.
We're gonna do that.
Actually, can you do me a favor?
If
And I
everything,
didn't raise
you
it up.
think you want to figure that out?
Can you go open up, Internet Explorer, go to Mercy College Blackboard, log in?
You see all the three courses.
Is your office down here or up at Dobbs or?
I have an office in Dobbs, I'm not there very often.
Oh, okay.
Well, you can check out Mercy College Blackboard.
If you go to the Mercy Connect, you know,
Space Blackboard.
so here it has notes.
Never mind, scratch that.
No, but then I don't want to do, you know.
What's the cheapest?
The rental thing. I like rental.
Ain't not that bad. I thought it was $90, Just to know about your work.
Okay, so, Bronx,
Okay.
so, everything is in of course, material. And then for your Excel, you'll go to Excel exercise data. You'll click on this first one. Should be download.
want to take it,
I know. I know that.
So this is like the first one,
that's what one of the guys.
say,
I said they might like,
find a name
turbo,
all those.
turbo, like, you know,
Yeah.
Say people, name that,
no, actually, Mike, the other guy, I seen him.
Yeah.
Yeah. You were taking it, right? Yeah. So early, you didn't know it was that. Right, so,
Yeah, I'll call tomorrow.
I did, I didn't write it down, I gotta do one of those, send it to me.
It's the same,
Okay.
once you do that, the black one, or everything, basically, for that, everything you do everything on black one.
Right, right.
Everything is supposed to
Right,
be,
just-
yeah, so it says it, and then everything is supposed to be.
Book on it. Like a ebook.
Right? Well, you can, it's cheaper to buy, you have that option, I just.
Oh, really? How much is that?
They got the.
Buy it on what?
No, like you go to
Amazon.
Amazon,
Oh, okay.
or Barnes and Noble, or,
I'm totally with it.
then,
Business.
there's Texas.com, Chef.com, so they all have that option.
That's
Yeah,
what
that's
I'm
the option.
School is like,
Yeah, it's like, so, Jada, they have all the, I think she have all the,
It's like night and day.
So then,
oh, who's it? No.
every book,
That's all right. What's up, bro?
Yeah, that's what I'm saying. That's what I'm trying to do. We're gonna be working together.
Is Richard here? Yes. Jadea Davis,
Jada, I'm here.
Jasnell De La Cruz,
Joseph, the Cruz, I'm here.
I just say here, I didn't correct me. Shamika,
On detail.
Gabriel, Barbara,
I'm here.
Mariani,
Here.
Omar, Andrew Morales.
Oh.
Yes, sir. Victor Quinzo. Nelly Santiago Rivera.
They here, they're down
Yeah.
ladies.
Raymond Smart. Raymond Smart.
Brandon?
Raymond Smart. Carlos. Present. Thank you. Okay. Derek Thompson. Derek Thompson's not here. Okay, so I'm missing Derek, Raymond, Victor.
You guys on do turbo? When will you guys do it? Oh, February. We all did it like together. Here, in July. Because all you know each other.
Derek's right there.
Hey,
He was taking attendance.
oh, that's me.
Derek's here?
Derek.
Oh, and
Okay.
Victor's here too. Victor's
Derek,
not sitting
Derek?
down.
Yeah.
Oh, yeah,
I'm back.
too, my bad.
Victor's here?
Victor's in the, yeah, he's,
Raymond here?
I don't know who
I
ran.
don't know, Ramon?
Only Raymond, okay. Not here.
Yeah.
Not here.
Yeah, me and Victor are here.
Oh,
What's that?
You're very welcome.
Just after class.
Yeah,
Well, you start working, so I'm gonna be after class.
and gentlemen, I'd love it when I'm able to get you out of class early.
Yeah.
Unfortunately, that's not gonna happen tonight. But I will get you out of class right at 9:30. Cool. For sure, I would never keep you out for 9:30. Unless I'm trying to tell a really funny story.
Okay, wait, no, I think I heard you.
What about it?
On my knees. All right. So, on the bottom of page 8, we found the normal distribution. You all calculated the most important discovery of history statistics. You did yourself. Congratulations. When we have this normal distribution, we know things about the characteristics of it. We know the probability that it's going to fall into, and we can do things like sampling for a very small number of people, like say 30, and be very confident that we've got a good estimation of the center of that data. As long as we know two things on the top of page 7. One, the expected value. 2, the standard deviation. The expected value is actually what we're sampling for. That's the average. If we played a game like, let's just assume we didn't know it, guess what it is, we would find out that it would be 10 in that experiment. The standard deviation is the spread, the distribution. All right, is this a fat bell curve or is this a really thin bell curve? Let's look at the bottom of page 9. That example is just picturified right at the bottom. What is the difference between these two frequency distributions? Take a look. We've got one that's really fat and one that's really thin. So what does that mean to you about the distribution of this data? Say we're doing the same thing 20 times. What would the one on the left represent? What would the one on the right represent?
My left hand.
Well, the one on the left would have a wider distribution, and the one on the right would be narrower and more.
Yeah, what does that mean, wider distribution or narrow distribution?
Big sample?
No, because you can have like a sample of at least 20 and still get those type of curves. So
Yes,
it's-
yeah.
So, give me a second.
Take it.
So it's just that the information that you've got in the first one has a wider spread, where you can have outliers.
Yes.
As opposed to,
Yes.
or you would have more outliers with the first bell curve as opposed to the second one. You would still have outliers, but the majority of your information would be more to the
More,
center.
yes, more people would get a 9, 10, or 11 on this tighter, thinner curve, right? In the fatter curve, we have more people getting like a 5, 6 heads, or 15, 16, 17, 18, 19, 20 heads. It would be higher probability with this fatter curve. Not necessarily. Yeah, I think if you actually look at the height, you would see that the thinner one is taller in the middle. So we're talking maybe like 70% of your data would be right within the 1 or 2. So, alright, so that's just the spread. So if we know the standard deviation, we know the mean, the center of it, we know it falls into a normal distribution, which is what we calculated. We know that it's going to follow normal laws of probability, then we know a lot. Because you can see these curves are symmetrical. Also, we're able to calculate the percentage chance of being in that top or up tail, the percentage chance of being in the lower tail. We're able to make those kind of assumptions when we can assume a normal distribution. Top of page 10 has got our normal distribution. Like I said, that we know those two things, the mean, which is that U letter, and the standard deviation, which is the O with a little hat on it, sigma. So the U is sometimes called mu. The standard deviation is sometimes called sigma. We'll just call it standard deviation. If you look at the bottom of page 10, two parameters, the mean, the standard deviation. The highest point in the normal curve is the mean, which is also the median and the mode. We'll talk about that in a minute. The normal curve is symmetric. 50% probability on the left, 50% probability being on the right. Key characteristic of a normal distribution, it is symmetric. Your probability of flipping a coin and getting 20 heads is the exact same probability of getting 0 heads, because they are polar opposites. Top of page 11, key normal distribution properties. So because we can assume normality, because we can do those calculations like you all did, we can tell how much of the data will be under which parts of the curve. Now let me just fire these 3 pieces of information at you, and we'll discuss what they mean. Number 1, approximately 68.3% of the data will be within 1 standard deviation of the mean. So within 1 standard deviation of the center. Approximately 95.5% of the values will be within 2 standard deviations. Approximately 99.7 will be within 3 standard deviations. So what that means is that we have our normal distribution, alright? If we know the mean, alright, and we know the standard deviation, we can say, alright, the mean is here, and 1 standard deviation, this is 1 sigma, 1 standard deviation, alright? I gave you a simplified example earlier. I said, what are the chances of being between 9, 10, and 11? That's an approximation. So 1 standard deviation, we don't know exactly what that number would be, but we know that there's a 68.3% chance of all the data being within that range. All we need to know is the mean and the standard dev. We also know that within 2 standard deviations will be 95.5%, and within 3 standard deviations will be pretty much all the data, 99.7. Because this bell curve follows mathematical principles the same way the binomial curve that you calculated followed. So not only can you calculate things like this, but you can also calculate what line marks the top 5%. Alright, what line marks the top 1%? Alright, if we know these 2 numbers, we can plug that in and find it. We're going to do some examples of this, and that may shed some more light on it, but I see some sparks, so I feel like you're at least with me so far. All right. So we've got the Z table here. How do I want to do this? So the Z table, tells us essentially percentage of the data that is within a certain number of standard deviations. Let me define Z-score for you before I go any further. So let's look at the bottom of page 12. You see that Z-score? Alright, the Z-score is X minus U divided by sigma. So X, which is a certain test statistic. U is the mean, the average, and that sigma sign is the standard deviation. So let's say in our flipping heads and tails example, you go home and you flip a coin and you get 16 heads. Alright, that's X. That's your test statistic. The mean, the U, is 10. We know the average, the expected is 10. We did the calculations. And let's just say we were to calculate the standard deviation, which tells us how much the spread is. Let's just say it was 3. Okay, so the Z-score for your experiment of 16 heads is going to be 16 minus the mean, which is 10, minus our standard deviation, which is 3. So 16 minus 10 is 6, divided by 3 equals 2. So what that means is you were 2 standard deviations above the mean. And the reason that's important is because we can define percentages on the standard deviation. We can tell you just how many people, what percentage of people were less than you on that standard normal distribution. So, I'm flipping around here a little bit, but I feel like I haven't quite lost anyone yet. So I'm going to keep going. Let's turn to page 13, and let's look at that example on the top. I've got a standard normal distribution. Right, I've got that curve, and I'm going to assume it's normal. I'm going to assume it's normal because I'm told it's normal, or because I've done some calculations and I can tell that there's nothing skewing the data. It's going to come out to a normal distribution. And I know that someone who does this experiment by, say, flipping coins has a z-score of 1.2. All right, that person is 1.2 standard deviations above the mean. So that means they flipped heads a few more times than the average person, such that when we calculated their z-score, we got 1.2. So I can look on the standard normal table, also known as the z-table, and I can say, well, what percentage of data is less than a z-score of 1.2? So, on the left-hand side, I look, it says z, the far left. I go down to 1.2. I would go across to the right. It's 1.20 is the number I'm looking for. If I were looking for 1.29, I would go all the way to the right. But I'm just looking for 1.20. So I see 0.8849. What that tells me is that 88.49% of the data is less than a z-score of 1.2. How do we get all these numbers? Well, someone did what you all started to do with those binomial calculations, where we could have calculated all 20 possibilities, counted up the percentages. Someone calculated not just 20, but every single possibility in between 0 on a stand and whatever on a standard curve. And they came up with percentages under the curve. The same way you all calculated, well, there's only a 1% chance of getting up and getting 20 out of 20 heads, or less than 1% chance. That means you're in the highest 99% chance. This is the same thing. It's just with every calculation in between. So, someone says they have a z-score. They're 1.2 standard deviations above the mean. That person, on a normal distribution, we know that since this distribution is symmetric, 50% is in the upper half, 50% is in the lower half. We know this person with a 1.2 z-score, we know that 11.5% of people are higher than her, and we know that 88.5% have a lower outcome than she did. Does that make sense? Okay. So, what I want to do now is I want to skip right to my go-to example, because I'm excited that you all seem to be with me, and I just want to put this in context with an example right away before I give you anything more complicated. Let's go to the top of page 15. Alright, suppose I have information on the average height of an American male. And I know the average height of an American male is 70 inches. And suppose I have information on the standard deviation, which means how diverse that pool is 3.5 inches. If every American male was very similar in height, then we would have a small standard deviation. If every American male was typically not the same height, then we have a larger standard deviation. But let's just say we have those numbers. We have the mean equal to 70. The standard deviation equal to 3.5. All right, suppose further Michael Jordan has a height of 78 inches. Is that above the average?
Yes.
All right, how much above the average?
2 standard deviations?
Yeah, something like that. 8 inches above, so 2 plus standard deviations. Tell me exactly how many standard deviations, and to answer that question,